Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 13, Organic Chemistry 2. Today we are going to continue on chapter 3, Reactions of Aromatic Compounds. In the previous lecture we talked about Introduction to Electrophilic Aromatic Substitution. Today we will cover Activating Group, Deactivating Group, Determination of the directing effect of a substituent, activation or deactivation by substituents on a benzene ring. We'll ask ourselves, what are the factors that contribute to activating or deactivating nature of substituent in the electrophilic aromatic substitution reaction? How do they make monosubstituted benzene more or less susceptible to further electrophilic attack? When we know that toluene reacts faster than benzene, faster than nitrobenzene in electrophilic aromatic substitution, what are the factors that contribute to that? The electronic influence of any substituent is determined by an interplay of two effects that, depending on the structure of the substituent, may operate simultaneously: induction and resonance. Induction occurs through sigma framework, taper off rapidly with distance, and is mostly governed by the relative electronegativity of atoms and the resulting polarization of the bonds. Resonance takes place through pi bonds. It therefore longer range effect and is particularly strong in charged system. Let's talk about inductive effect. When we have electron donating group, increase the electron density on the benzene ring, such as alkyl group, are donating by virtue of their hyperconjugating sigma frame. On the other hand, if we have trifluoromethyl, it is electron withdrawing group. Electron withdrawing group. Okay? Similarly, direct bound heteroatoms such as nitrogen or oxygen or halogens. Okay? Also, the group which has partially positive charge directly connected to benzene ring. Okay? All these groups are electron withdrawing group. Okay. Let us turn to substituents that resonate with the pi system. Resonance donor bear at least one electron pair capable of delocalization into the benzene ring. Therefore, such a group, amino group or alkoxy groups, and halogens belong to this category. Okay? They have negative inductive effect. By resonance, they are withdrawing electrons. But resonance, okay, resonance will be a positive. So it has negative induction, positive mesomeric, okay, which are opposing each other. But which one prevails? Which control the molecule? The answer depends on the relative electronegativity of the heteroatoms and on the ability of their respective p orbital to overlap with the pi system. For amino and alkoxy group, resonance overrides induction. But for halogens, Induction outcompetes resonance, making them weak electron donor. They can't easily give out their lone pair. Mesomeric effect. If we have, as we mentioned, group substituent with lone pair, see how they increase the electron density. See, they increase the electron density on the benzene ring, right? Group such as amino or disubstituted amino group, alkoxy group, halides. On the other hand, we have another group with negative mesomeric effect, negative inductive effect, like aldehyde ketones, nitriles, nitro, sulfonates. All this group has both induction negative, mesomeric negative. Let's see, they decrease electron density by mesomeric as well as by induction. Do they affect the direction of the electrofield on the ring? Yes, directing effect. A group can direct electrofield toward ortho, and we have two positions for ortho. We have two positions for meta, and we have one for para. And the controller here is this group. We call it directing group. Ortho and para directing. Directing inductive effects of alkyl groups. Electrophilic attack at the ortho of the and para positions produces an intermediate carbocation, tertiary, secondary, and secondary carbocation. Let's see in here, if we attack in here, so this will be connected to the electrofield, positive charge will be on that carbon. This is tertiary. Delocalization, resonance will move the positive charge in here, then in here, and we have now three carbocation, tertiary, secondary, secondary, right? If we move to meta directing this way, so the E will be connected to this carbon, and this will be positive. This is secondary, and this is secondary, and this is secondary. So the contribution will be secondary, secondary, secondary in the intermediate. Which one is more stable? This one or that one? Of course, tertiary, secondary, secondary. Now let us go to para position. Attack this way. So the positive charge will be on this carbon, secondary, tertiary, secondary. So the contribution here would be secondary, tertiary, and secondary. Again, this is much more stable than the meta one, equal to the one in the ortho, right? So the alkyl group is also para director, ortho para directing group. If they are the same, why sometimes, most of the time, you get para and ortho not formed in equal amount? The answer is the steric effect. If you have a bulky group, you have para product more than ortho. If we compare, this is activating group. If you compare the stability of the intermediate first step, rate determining step, you find in benzene is high. When you compare that to the methyl benzene, toluene, you will find that the ortho lower in energy, it's equal to para. If it's a little bit bulky, then you may say it's a little bit here, so you get more product para position, and the meta will be higher, so you will have the product ortho and para. Experimentally, toluene with bromine in presence of iron-3 bromide gives 40% 1-bromo to methyl benzene and 60% 1-bromo 4-methyl benzene and traces of meta around 1 to 2%. Okay? Why para more than ortho? As you can see here, this is the methyl and this is the bromo. There is a steric factor. See here, the bromo here and methyl far away, so there is no steric factor in the transition state. Okay? Let's see one more. This is bulky group, right? And if we try to make Friedel-Crafts acylation using zeolite as a catalyst, we get 96% of the para product. Also trace. Again, you can see that here no steric factor, but here there is a steric factor in the ortho positions. Okay? Directing mesomeric effects of heteroatom with lone pair. Okay? The ortho and para attacks give intermediates with 4 resonance form. Okay? While in case of meta, there is only 3 resonance form. So which one will be more stable intermediate? Of course, ortho and para. So if we attack here again to form ortho, you will have here carbocation. This can resonate in the ring, form this and that, or the lone pair will come down to form an extra resonance form, which stabilize the ortho and para positions. Okay? In case of meta, the positive charge will be in here, delocalize will be in here, one more resonance structure will be in here. Only 3 resonance structures. Okay? That's why the mesomeric effect, positive M, led to the formation of ortho and para products. Nitration of anisole nitric sulfuric mixture led to the formation of 30% ortho-nitroanisole, 65% para-nitroanisole, and traces of meta-nitroanisole. Why ortho 830 and para 65? It's clearly again its steric factors. Here is the ortho and here is the para. That makes the transition as well as the intermediate in case of para more stable than nitro in ortho. So para isomer will be more stable than the ortho isomer. A methoxy group, we call it strongly activating. Why? Because when we treat anisole with just bromine in water, we get the tribromoanisole. If we consider the naming that anisole, so this will be number 1, the bromine will be number 2 and 4 and 6. So it's 2, 4, 6 tribromoanisole. If you would like to name it as a benzene, then it will be 1, 2, 3, 4, 5, and that will be 1,3,5 tribromo, 2 methoxybenzene. Well, the product in this case 100% tribromo compound. So methoxy group is strongly activating. As well as aniline NH2 is strongly activating. Why? Treated with bromine in water, you get the tribromoaniline. Phenol, again, OH. In phenol, add bromine water, you get tribromophenol, 100%. So, because of their high donating activity, aniline and phenol undergo substitution reactions with iodine, a halogen that is normally unreactive with benzene derivative. So you react aniline with iodine and sodium bicarbonate, you get the para iodo compound, okay, and good yield. In addition to overactivity, the Friedel-Crafts reaction employing aluminum chloride as a catalyst does not work with aniline because this is good donating group NH2. It will react with Lewis acid aluminum chloride to form this complex where you have here N as a positive charge, so became electron withdrawing group and deactivating group. So the reaction will not go, and it needs a different reaction condition. So we cannot say that Friedel-Crafts reaction will not go. No, it will go, but will not use alkyl halide and aluminum chloride. Okay. To slow down the reactivity of NH2 group, we acylate to form N-phenyl acetamide analog, okay, replacing H with C double bond O. So this group will take the lone pair into the C double bond O electron withdrawing group. So it will control its reactivity a little bit. So when we nitrate this molecule in nitric sulfuric at almost room temperature, you get N2-nitrophenyl acetamide and N4-nitro para position and ortho position and traces of meta Why should phenyl be weakly activating and still also para directing? If you look for the ortho para attack, if that is ortho, so this will be connected to the ortho and positive charge in here. When we have a positive charge in here, it can be delocalized into the other ring, positive charge, and we will end up with 6 resonance structures. Okay? You can try it yourself. In meta, when you get this carbon connected to the electrophile, the positive charge will be on that carbon, or in that carbon, or in this one. So it will not delocalize on the other one, and only we will end up with 3 carbocation intermediate in resonance, right? 3 resonance structures. So the ortho will be more stable. Para will be the same as ortho. 1, 2, 3, 4, 5, 6, 6 resonance structure. That's by resonance. Even though the phenyl has negative inductive effect because the carbon here is sp2 carbon. Deactivating ortho and para. The halogen. The halogen has electron withdrawing negative inductive effect, but it has a positive mesomeric effect. They are opposing each other. The mesomeric effect makes 4 resonance structures for the ortho and para, while only 3 resonance structures in the meta intermediate. So which one is more stable? Ortho and para. But inductive oppose the mesomeric, so it will not be activating, it is deactivating. It is deactivating. When we have bromo, benzene, we add bromine in iron bromide, we get ortho in 13%, we get meta in 2%, we get para in 85%. Meta directing inductive effects of electron withdrawing group. If we do the ortho, we will find that we are creating here a positive charge on the electron withdrawing group attached to it. So this resonance structure will be highly unstable, very poor contribution. Okay, and here we have a resonance to delocalize the positive charge on this carbon and that one. So mainly we have 2 resonance structure, 1 very poor contribution. On the other hand, if you look for the meta, you will find that the carbocation is located on carbon far from the electron withdrawing group. So we have here 3 resonance structure. In para position, we have this one, that one, and that one. Again, this one positively charged carbon carrying the electron withdrawing group, highly unstable. So mainly we have 2 resonance structure contribution and one very poor. So the meta intermediate will be more stable than the ortho and para, leading of course to meta product. In a strongly acidic solution, benzamine aniline becomes less reactive to electrophilic attack, and while para attack is still dominant, increased meta substitution is observed. Explain. Well, to explain that, in acidic medium, aniline is protonated to form the anilinium ion. The anilinium ion is meta-directing group. That's why beside the ortho minor, very minor, and para major derivatives, significant amount of meta derivative is also formed. So if we react that with nitric sulfuric acid mixture and work up with base, you will get the para nitro aniline 51%, meta 47, and also 2%. Aniline will get protonated to form anilinium ion. This is meta-directing group. Since the aniline is highly activating group, the NH2 is very activating group, so it will react to form the para and minor, very minor ortho. Why the ammonium group here is meta-directing? Because it's electron withdrawing group. There is no mesomeric effect. There is no lone pair on the nitrogen anymore. So this carbocation will be poor contributor. In the para again, poor contributor. And the meta will be major in this case. Directing mesomeric effect of electron withdrawing group. When we have a group with partially positive in here, okay, which has a negative inductive effect as well as has double bond, so it can also, beside negative inductive effect, will have a negative mesomeric effect. Destabilize the carbocation here by having this positive charge adjacent to carbon positive. That's highly unstable. In meta, this is not the case. In para, we have one, yes. This is carbon plus adjacent to carbon plus. That's highly unstable. That's why the meta intermediate will be predominant. Here we have benzoic acid, nitrate benzoic acid, nitric sulfuric. We will get ortho 18.5, meta 80%, and para will be 1.5%. See you in next lecture.